Microwave technology has promised to be the next big thing for industrial chemical processing for almost half a century. Processors recognize microwave's potential to limit their carbon footprint and cut operating costs by reducing energy use. In the grease and lubrication specialty, the University of Northern Iowa Ag-Based Lubricant Center, or UNI-NABLE, is poised to develop a new class of products based on microwave processes. UNI-NABLE has done more than 20 years of research in the formulation of bio-based lubricants and greases with vegetable oils. The research has led to the development of non-toxic and renewable eco-friendly compounds using conventional and genetically enhanced vegetable oils from oilseeds such as soy, canola, and sunflower seed. These products are made and marketed at an Iowa-based commercial company established through the university's research foundation called Environmental Lubricants Manufacturing, or ELM. Today, more than 30 bio-based grease products developed at UNI-NABLE are available in major U.S. retail stores under such labels as Soy Lube, Ultralube, and Lubra Magic. To help design and develop production-scale reactors for new microwave processes, UNI-NABLE added 2 more Iowa companies to the team, Amtech Microwaves and Marion Mixers. For over a decade, Amtech has achieved worldwide recognition for its microwave systems. Marion Mixers is a world leader in the design and manufacture of industrial mixing and drying equipment. The 2 companies have been working together since 2011 on a unique combination of microwave and mixer, making possible the uniform heat distribution that will be a huge advantage for the biolubricant sector. The collaboration of UNI-NABLE and ELM, along with Amtech and Marion Mixers, has overcome several long-standing challenges to using microwaves in the production of greases and lubricants. First is the misconception that microwaves cannot be applied to metal vessels. In fact, microwaves can be applied to products in metal vessels as long as the mass of product and the intensity of microwaves are matched. Arcing takes place when too much energy is applied for a given mass of product in the vessel. Second, both microwave and conventional heating methods cause damaging thermal oxidation, but the damage with microwaves is less severe. Another challenge is the very different and sometimes unpredictable behaviors of different greases under similar conditions. For example, some mineral-based grease products such as lithium tend to completely liquefy, making them easy to pump and circulate when heated in a microwave-based reactor. But other mineral-based grease products consisting of aluminum or calcium thicken during reaction, so they need mechanical mixing as well as circulation. The vegetable oil products developed at UNI-NABLE behave still differently because microwaves heat vegetable matter differently than they heat mineral matter. This is because microwaves are not really forms of heat, but rather forms of electromagnetic energy. They act like heat through their interaction with materials that absorb or reflect energy. Vegetable oils are dipolar and tend to absorb microwave energy, while mineral-based or petroleum oils reflect most of the applied microwave energy. One way to improve the heat absorption of mineral oils is to mix them with dipolar materials. Faster and more even microwave heating also leads to significant cost savings, starting at the chemical level because it achieves a more complete reaction. But microwave heating overcomes the limits of conventional heating in several other ways. Typically, fuel, oil, gas, or electricity is used to heat a transfer oil, which is then pumped into the jackets of a vessel containing the products being cooked. The open kettle is a slow process. Surface heating can go only as fast as allowed by the specific heat, thermal conductivity, density, and viscosity of materials being heated, and it's not uniform. The surfaces of the hot plates and jacketed kettles, and the materials in contact with them, do heat up, but the materials at the center of the kettle does not heat as quickly. Surfaces get sticky and the edges and corners of the product overheat, leading to possible product rejection, wasted energy, and extended process times. But with microwaves, the entire volume of a material heats at the same rate. The direct coupling of energy into the material is called volumetric heating, and overall it can reduce heating times, and because vegetable oils absorb microwave energy more effectively, drying temperatures can often be set lower for more savings. In other words, with microwave cooking, materials heat more rapidly and evenly and at a tiny fraction of the cost of conventional systems. But that's not all. Microwave technology saves significant energy in other ways. Microwave energy heats only the desired material, not the whole room, eliminating harmful greenhouse gas emissions, both from the heat source and the ensuing need for cooling systems. Using electromagnetic energy also means equipment doesn't have to warm up and cool down, saving money by reducing energy use and batch times. Neither does the material being mixed need to warm up or cool down much from its optimum temperature. Industrial microwaves can be adjusted very precisely from 0 to the maximum power output. A programmable logic controller, or PLC, is used with temperature sensors to form a closed-loop circuit and maintain the temperature of the product at exactly the desired level. The PLC expends only a few kilowatts of power to hold the product within a degree or two of the target temperature. Production-scale reactors are required for these new processes to capitalize on the advantages of microwave heating. The team of UNI-Enable, Amtech, Marion Mixers, and ELM are developing those reactors. The group began by studying various oils and the impact of their physical properties on their heat absorption. They also tested the effects of using different vessel shapes for processing. The first test unit used an 800-gallon, non-agitated stainless steel tank. The product was circulated using a series of jets and a single propeller agitator. The power source to heat the product was a 75 kilowatt industrial microwave transmitter. Mixing quickly became a major issue, and ELM tested many levels of microwave energy and variation in the speed of the circulating pump. Adjusting the agitation led to success. The Marion horizontal mixer with gentle agitation and Amtech microwave system made aluminum grease in much less time than it takes to produce the same product in a conventional jacketed kettle system. Marion Mixer's unique paddle-style agitator system can handle any type of products to be heated by microwaves, including solids, liquids, and grease-like semi-solid materials. The microwave mixer heating system is available in virtually any vessel size for any industry where consistent energy-efficient volumetric heating application is required. By using the Marion Mixer's microwave-based vessels, you can reduce your energy needs, speed your process time, improve the quality of the finished products, and have a more complete reaction in any chemical process that requires heating. Other benefits like smaller footprint, flexibility of location of the heating source, and reduced cost of the heating vessels add further icing on the cake.